Hello, everyone. My name is Myna from IBS Math, and I'll be presenting a wearable-based aging clock associates with disease and behavior. So let's begin to read the abstract. Any thoughts on the abstract? Maybe the gap sentence or sentence that's like the main statement.
I think there's no explicit gap, but they just mentioned that some efficiency for using wearable data-based age.
I agree. So I think the implicit gap is like current aging biomarkers use blood vitals and images, but they develop PPGH, which uses wearable device to measure your aging clock. So if we first begin, okay. So let's say we have these two people here, one, person two, different people, but they have the same age. We call this the chronological age when you were born. And let's say one person exercises a lot and it's very healthy. So they stay a very healthy lifestyle. And person two drinks beer or like smokes, doesn't continue a very
줌으로 탭 바꿔서.
그래. So these two people have the same age but has different lifestyles. So they usually have like a biological age. So person one can have 27 because they stay very healthy, and person two, their biological age can be much older. So if you stay healthy, you age slower, and if you don't, you age faster. And these usually you have these tests, and these can be got from the blood test, vitals, and DNAs. And this paper was asking if we can measure the biological age with the wearable device. So one of the data from the wearable device they used was PPG. It measures changes in blood volume using light. So this is a very brief diagram on how it works. So there's a laser here, here, and then it kind of shoots the light. And then based on the pulse wave or how much it reflects, it detects how much blood flows in your body after a pump of your heart. So your data can look like this, and mostly PPG can find your heart rates or SpO2. So first, with this data, I kind of want to define the goal of what we want to do with PPG. So we want to make sure that the model can learn PPG characteristics that are consistent within the same individual and distinct across different individuals. So these are all 3 different time series PPG data, and we want to make sure they capture the uniqueness of each person. And with that, can this information obtain biological age? And the main pipeline of this method, they used an algorithm called self-supervised learning, SSL. So to begin, I will tell you like how the input kind of works here. So they kind of make like a segment for each timeline. So each of them are 60 seconds. And for one person, they get 2 inputs like that. So you get 2 different time segments for one person. And then for the second person, they get another 2 different time segments. And then for the last one, they also get 2 different time segments. And then this is what we call the unlabeled recorded biosignal, because we don't know any information about their age or their like disease. So with SSL, what the algorithm do is we first augment the time series and embed the time series within encoder. So this is a brief example from Yumin's journal clump for last year. So this is how the augmentation module works. So let's say we have the original data set that looks like this. With this cutout augmentation, it'll like put random time or zeros here. And then for this magnitude warp, it'll it'll like multiply a function of like a smooth curve to the original time series. And then Gaussian noise, it includes small noise to the original data. And lastly, it also has like a time warp where it kind of give noise in the time shifts like this. So what this module does is yes. So maybe like they
use space step by step from the up, down.
The cutout is basically putting just zero, no values on like certain positions in the time series. And then magnitude warp is with the original time series, it multiplies like a very like slight curve to the original time series. And then Gaussian noise, it just adds in like a slight noise to each of the values in the original time series. And then time warp is like for certain values, it like shortens the parts, and for like other parts, it like extends the part, stuff like that. So in this augmentation module, what they do is they like pick random combinations of the augmentation options. So let's say for the top signal, they randomly choose cutouts and Gaussian noise, and they apply this together to get the augmented biosignal. And then for the second one, it randomly chooses like different augmentation options. And then it gives you a biosignal. And then they repeat that for all the input time series.
So how many numbers of augmentation did they choose? 2 or 3 or 4?
That's all random every time they run it. Sometimes they would have one augmentation, sometimes they would use all of them. So each of them has like a probability of if they will get chosen or not. So by doing this augmentation, it kind of encourages to like take out the noise, like timing and signal distortion. And that is why SLSL chose to try this. So this is what we have done so far. So we have the original time series, augmented, and then gotten the augmented biosignal. And now what we do is we apply an encoder. I won't go too deep about the encoder, but what this does is it extracts data into low dimensional representation. So if like we have a time series here, it'll have an embedding representation, just like a vector that represents this time series. And we want this embedding representation to distinguish physiology across different people. So if we have the same person, their embeddings should be close to each other. And if they're different people, the embeddings should be far apart. So it'll look something like this, where they attract the positive pairs and they repel the negative pairs in the representation subspace. So how do we know if they are a good representation? So how do we know if these are the most ideal representation? Is that they use a loss function called info NCE that I'll explain later. So they will kind of update the encoder so they minimize this loss function. Okay. So I will give a very easy, like a toy example about like how this algorithm kind of works. So let's say that our embedding representation are shown like this. So the H, if you look at the H here, the I is the person ID. So they're both I, and then one is just time series one, embedding one and embedding two, and so on. So if we kind of graph this in like a representation subspace, it'll look something like this. So if we look at it visually, like the different people are together and the same people are kind of far apart. So if we check this with the loss function, now we will look at the equation. What the numerator does, it minimizes the same ID embedding distance. So they want the same IDs together. And the reason why it minimizes is because there's a negative here in the loss function. And then the denominator, it wants to maximize the different IDs. So the blue and the pink maximize their distance. And how do we know if it's a different ID is because they put this condition where they have to be different when they're iterating the IDs. So everyone. So if we kind of expand this together, you'll get something like this part is the blues should be together, minimizing the blues, and then maximizing these, and then the top blue and top pink. And this is minimizing these two, and then this should be again maximized. And with the example, I just plugged in the numbers and we get our loss value like this. So we can kind of say that this can't distinguish physiology from the same person. And that is why the encoder will go through some hyperparameter to just update the parameters in the encoder to make it better, to make the representation space better. So another example that I can give you is something like this. So this one visually looks very nice, where the same people are clustered together. And if we apply this to the same formula of the loss function, then we will be able to get a very low loss value. So then this, we know that it can distinguish physiology from the same person. And this accomplishes what's called a pre-training test. So it learns participant level physiology. So now we have our pre-trained self-supervised learning task like this. So now what we do is this part is where you actually find the PPG age. So what we do is we have our healthy population. So they specifically in the paper defined it as the healthy population. And then they have the time series for 30 days. This. And now this part is a little different because now it's not unlabeled. It's labeled recorded biosignals, but because now we're going to add a feature with their actual ages. And then with this time series, what we do is we put it in the encoder and then outputs the embedding representation like before. So now we know that this encoder is like, it works well. We're just gonna freeze it and then put this time series into the encoder and then out here. Does that make sense? And now what they do is they fit a linear regression model predicting the chronological age from the embedding phase, like this. So it's a very simple model. And then what they do is they predict the age from the beta that they got when they fit it.
So how did they define the healthy? Did they just use some criteria related to just heart, or did they consider other features related to some like sleep patterns or something else?
It was self-reported. So they had some like medical criteria, but if they like marked as certain parts, they treated them as like the healthy cohort.
You explain the reason why they use augmented biosignal as a.
So this part, it's a very like general pipeline of self-supervised learning. So a lot of self-supervised models go through augmentations like this. So I don't know like all the details, but it does like it tries to make the model not focus on the noise, but to only detect the signals and like no other different times and distortions.
That means they generate multiple of a single.
Not multiple. So for this time series, they would like choose, let's say these two, and then make one augmented time series.
From a single unlabeled recorded biosignal.
Yes.
This is.
Did they have lots of younger people?
They had like how young? Like baby?
Huh?
Baby.
I know, like 20s or 30s.
They had some, like, they subgrouped them into like ages, and they did have some younger people, like up to 18 and older. So basically, you're basically fitting the healthy population to the healthy time series. So if this fits well, it's basically saying that like you're healthy, you're in the healthy population. So this predicted age is basically the PPG age, the biological age. And now what they do is with the PPG age and then the chronological age, they compare the two. So what they do is they find the gap. So the difference between the PPG age and their actual age, and then the rates, and then time series per day. So if the gap of the PPG age is bigger, it just says you're older. And if they're younger, if it's less than 0, it's showing you're younger. So if we look at the results here, so the colors of the points here are showing the PPG age gap. So if they're red, it means you look older, and if they're blue, it means you look younger. So if you look at it like this, the population with high PPG age gap has a higher relative risk compared to people with a lower PPG age gap. So you can be seen like this. And then with all the different diseases, they also showed the relative diagnosis rate as well. So if you look at it here, all the people who looks old are kind of shifted like this, and people who appears younger or has a less relative diagnosis rate. The same with the males as well. So the higher PPG age gap showed higher diagnosis in multiple disease. And another analysis that they did was, if you look at the gap here, the y-axis is the PPG age gap. So if it goes higher, it means that you look older. And then this red line, you can see that these are the people who smokes every day, and these people have the higher PPG age gap. And then similar with exercise time, but opposite. So people who looks younger tends to exercise. I mean, people who has a high PPG age gap doesn't really exercise like this. Just like this. And then the higher PPG, it also has bigger REM latency. So they also did some analysis based on the Apple Health app. So these are some analysis that they did. And then they also did some, if you look at the age time series, we can see the change in PPG age when a disease event starts. So if you look at the valve replacement here, this is when it starts, and their age gap tends to increase a lot and then decrease. And then increase when the heart failure starts like this.
What is valve replacement?
I think it's like some part of your organ. replace. Okay, so lastly, I didn't expect my slides to be this quick. Sorry. But what they basically did was they trained the unlabeled data from the recorded biosignals, and then they encoded to have the most ideal embedding representation. And then they fit it into the healthy population in order to get the predicted PPGH. And that is all.